today's lesson, we're going to look at another gas law. This one's called the ideal gas law. So this gas law is different from any of the others that we've seen so far because it actually includes an amount when we're dealing with chemical compounds. So the other ones just dealt with volume and temperature and pressure. So now we're including those things along with moles. So this is the ideal gas law. PV is equal to nRT. So let's take a look at the conditions. So temperature is in kelvins, mass is in moles, volumes has to be in liters, and pressure is in kilopascals. And then there's this other variable called R, which is the universal gas law constant. And you can see it in different units, but we're going to look at it mostly in these units because these are our standard conditions. The value of R is 8.314, and the units combine all of the units from all of the other variables. It's kPa times liters over moles times Kelvin. Now it might seem a little bit overwhelming at first, but we'll take a look at how you get R and where those units come from. R is considered to be an exact constant. For us, we're going to express it with 4 significant digits, but if you include less rounding, of course, you can have more than that. So why does the gas law constant get those variables? Well, if we take this formula and we rearrange it, if you just looked at R, you would have PV over N times T. If you put in all of the variables at STP, you'll be able to get this R value. So P is pressure, kPa, V is liters, and then underneath in the denominator you have moles times temperature, so moles times Kelvin, and that's where those units come from. This is a constant value. If you had a written test or evaluation and you needed the R value, you would be given that in a question, so you don't have to memorize it. But after you use it a few times, you'll probably notice that you remember it. So let's try out a straightforward problem with the ideal gas law. And then in the next lesson and later on today, we'll look at some applications of the ideal gas law. So we've got a light in a flashlight. The bulb contains 2.4 times 10 to the negative 4 moles of oxygen gas. It's at 1.9 atmospheres and 19 degrees Celsius. And we want to know what the volume of the gas is in the bulb in milliliters. So these questions, you should notice, sound similar to others, but the big difference here is if you see anything with mass or moles, you have to think, I'm dealing with the ideal gas law. So let's start writing down our variables. We've got 2.4 times 10 to the negative 4 moles of oxygen gas. Our pressure is 1.9 atmospheres. And our temperature is 19 degrees Celsius. And what we're trying to solve for is the volume. And we want our final answer to be in milliliters. So when you look at these variables, moles, pressure, temperature, volume, that's where we have to think, okay, I've got to use the ideal gas law. So PV is equal to nRT. That means I have to use my R value. So if you want, let's take a look at that again, 8.314 kilopascals times liters over moles times Kelvin. And so when I look at my R value, I want to check, do I have all of my variables over here in the right units? kPa, this is not in kPa, so I'm going to need to change atmospheres to kilopascals. Liters, when I use the ideal gas law formula, my answer will be in liters, so I just have to remember to change it to milliliters at the end. Moles and moles. and Kelvin, oh, and here's Celsius. So before I can do anything else, I need to make sure that I can convert my pressure and temperature into the correct units. So this is something you should be able to do. So pause the video and see if you can convert pressure into kilopascals and temperature from Celsius to Kelvin. Once you've done that, unpause and we'll keep solving the problem together. All right, so hopefully you gave that a try. So when you convert your atmospheres into kilopascals, you should get about 192.47 kilopascals. And for temperature, 292. Again, if you're not remembering how to convert those, go back to our previous lessons where we did those conversions. Now we can start to solve the problem. Since we're solving for volume, we're going to rearrange our formula. So this is the standard format for it. We want to solve for volume, so we need to isolate it. It's already on the left-hand side, which is nice. I need to move pressure away. So if I'm moving pressure, it goes from numerator on the left-hand side to denominator on the right-hand side. And so my rearranged formula should look like that. For this one, we don't have to do a lot of rearranging for. Once I know what it is, I can start to plug in my variables, and we're going to put all of our units in like we always do to show how they cancel. So 2.4 times 10 to the negative 4 moles times 8.314 kPa liters, moles times Kelvin, and our temperature, and that's all divided by our pressure, which is 192.47. So let's take a look at the units and how they cancel, and then we'll look at our final answer. So moles in the numerator, moles in the denominator, that will cancel. Then we've got kilopascals in the numerator, this is in the denominator. And then Kelvin numerator, Kelvin denominator, and the only units I'm left with are liters. So that worked out. So now that I go to calculate my volume, I'm going to plug everything in my calculator, and my answer, remember, will be in liters. So when I do that, I should get about 3.027 times 10 to the negative 3, and you can double check this in your own calculator, and that should be in liters. But remember, the question wanted us to report in milliliters for our final answer, and we'll need significant digits. So liters to milliliters, we're going to multiply by 1,000, and when we look at our question, we should only have 2 significant digits. So here, when I round my answer, I should get approximately 3 milliliters of oxygen gas. So there's lots of problems you can do with the ideal gas law because there's lots of variables in there. You can modify the moles to include mass and molar mass. You can include density. So you'll see that in the next lesson. But for now, most of the questions involving ideal gas law will just have moles or mass and some related problems to it. One other application of looking at the ideal gas law ties in with a concept called molar volume. Now you might think, okay, I know molar concentration, molar volume is similar, but not exactly the same. So the first thing we need to understand before we look at molar volume is something called Avogadro's hypothesis. You should remember Avogadro back when we learned about number of particles and counting moles and Avogadro's constant. So when he was looking at particles, he was also studying gases. So he recognized the molecule is the smallest part of a gas. So an oxygen molecule, hydrogen molecule, whatever that is. But he realized through experiments that if you have equal volumes of gases, didn't matter what gases they are, the same volumes of them, and if they were under the same temperature and pressure, it means they would have equal numbers of molecules. And so that's important because now recognizing that under certain conditions, you'll have the same number of molecules in the same volumes, and that we can use to calculate molar volume, which you'll see next. Another way of thinking of it is tying in it with mole ratios. So if you had a balanced equation, you could also apply that as well. If I have 2 here, that could mean I have 2 moles of hydrogen gas. 1 would mean 1 mole of oxygen gas, and a 2 would mean 2 moles of water vapor. But if we tied in with Avogadro's constant, they fall in the same ratios. I could say this is 2 molecules of gas, this is 1 molecule of gas, this is 2 molecules of gas. I could scale that up if I wanted. I could say this could be 20 molecules of gas, 1 molecule, 10 molecules of gas, 20 molecules of gas here. Or I could even tie it in with volume. I could say 2 milliliters, 1 milliliter, 2 milliliters. All of those would be able to be related because if you have the same temperature and pressure, the volumes and gases will have equal numbers of molecules. So now let's take a look at molar volume in a little bit more detail. So first, what is molar volume? So molar volume is the space that 1 mole of gas occupies. How do we express that? It's in liters per mole. So it's not moles per liter. Mole per liter is molar concentration. This is molar volume. How much volume or space does a gas occupy per mole? If you look at STP conditions or SATP conditions, you'll always find, because according to Avogadro's hypothesis, 1 mole of gas will always occupy the same volume. At STP, it's 22.4, and at SATP, it's 24.8. And we'll do a calculation in a minute to see how both of those work. But that ties right in with Avogadro's hypothesis. We keep the same temperature and pressure conditions. If we have the same amount of gas, it's always going to occupy the same volume. So what does a molar volume formula look like? In just simplest terms, we look at the units. Liters is volume, so volume in the numerator and moles in the denominator. But now that we know the ideal gas law, we can combine our molar volume formula and the ideal gas law to come up with another way to express molar volume. And we can use that to show how 1 mole of gas at STP is 22.4 liters, or what happens at SATP. So first, what we're going to do is combine some of these variables. So you can see volume and moles are present in both formulas. So what we're going to do is start to manipulate our ideal gas law. So what I'm going to try and do is get volume divided by moles over here on my left-hand side of the equation. So volume's already here in the numerator where I want it. So I'm going to move my pressure to the other side. It goes into the denominator. And then I can see now I can move my moles. I'm going to move my moles from numerator to the denominator on the left-hand side. So I'm left with RT over P. And here you can see I've got volume over moles, which is here in my molar volume formula. So now what I'm going to do is I'm going to rewrite this, but instead of writing volume in moles, I'm just going to put in molar volume. So my molar volume can also be equal to the gas law constant times temperature over pressure. So this is another way you can also express molar volume. Now up above here we showed at STP, 1 mole of gas occupies 22.4 liters. This relationship is always true. How did you come up with that number, you might wonder? Well, let's plug it into this manipulated formula that we just came up with and do that. So remember, STP pressure is 101.3 kPa, and the temperature is 0 degrees Celsius, which we know is 273 Kelvin. So if I take those measurements and plug them in here with my gas law constant, I will get 22.4 liters per mole rounded. So let's show how that works. So molar volume, we're going to take our gas law constant, multiply it by the temperature, and we're going to divide it by the pressure. Let's take a look at our units. Kilopascals numerator, kilopascals denominator. Kelvin in the numerator, Kelvin in the denominator. And our units that are left are liters over moles. That's for molar volume, so that's great. So now plug this in your calculator, and we'll round to 3 significant digits here, and you should see that you get 22.4. So try to plug it in your calculator and see what you get. All right, so when you do that, you should get 22.4 approximately, and the units are liters per mole. So it doesn't matter here what type of gas you have, because you can notice that the molar part has been completely removed. The volume here has been completely removed. Any gas, as long as the volume doesn't change, under STP, same temperature and pressure conditions, will always have the same molar volume. You can also apply this with SATP and confirm what the molar volume should be for any gas at this condition. So I'm going to get you to try this one yourself. Remember, SATP conditions are different. The temperature, if you remember, is 25 degrees Celsius, and the pressure is 100 kilopascals. SATP is more commonly used to standardize more working conditions, like in a lab, because you wouldn't generally be working at 0 degrees Celsius. You're closer to room temperature, which is lower 20s in Celsius. So I want you to try and go ahead, try and use our manipulated molar volume formula and see if you can solve for the molar volume of any gas, this time under SATP conditions. When you're ready to check, unpause, and we'll walk through the answer. Okay, so hopefully you gave this a try. Let's start taking a look. So remember, this is our manipulated formula. Molar volume is equal to R times T divided by P. We're going to plug in our SATP conditions. 8.314 times 298 divided by 100. When we look at the answer, this is unrounded. It's 24.77 and a few extra digits, liters per mole. And if we round it to 1 decimal place, which is common for reporting, you get 24.8 liters per mole at SATP. So if you're dealing with gases and you have those conditions, you can use molar volume as a ratio, just like you would a mole ratio, to help you figure out amounts or volumes of moles under different conditions.